Hi gang. Okay, welcome to week 10 and the week 10 written assignment, all about exponential modeling and working with exponential functions, and in particular using logarithms to solve exponential equations when you're working with exponential functions. So let me give you a video or two here just to get you into this activity and get you into these fairly challenging problems in this last week of new material. Let's start with just an exponential equation where we don't have the convenience of being able to use the common base method. Solving exponential equations using logarithms. So in the past we've solved stuff like, something like this where the two bases could both be written in terms of base 2 or base 3 or base something, and it was possible to solve that equation without any other technique. I want to make this more interesting now. What if we're trying to solve 8 to the x, but then our other base is not so compatible, 8 to the x equals 13. Harder, right? And in general, more realistic. You've got to solve an exponential equation, an equation with an exponential expression in it, with x in the exponent, but you've got, nastier numbers that you can't write in terms of a single exponential base. What we're going to do with these is take a logarithm on both sides. And what's kind of cool is a lot of the times the log base doesn't matter so much. So here I used log, that's log base 10, right, the common logarithm. And of course if 8 to the x is equal to 13, the log of 8 to the x will be equal to the log of 13. And what's powerful about taking a logarithm on both sides is then you can use this very handy property of logarithms that says that the power inside the log argument is the same thing as just a multiplier, x times the log base 10 of 8 over here, right? That third property of logarithms. So logs let you get the variable or the variable expression down out of the exponent position and down written on the line. And then just keep in mind that log of 8 is just a number. It's the power you raise 10 to get 8. And log 13 is the power you raise 10 to get 13. They're just numbers. So you can solve this equation now by dividing both sides by log 8. Like you could divide by any number to isolate x. And you get this as an exact solution. In most of the settings in this week, you're going to be looking at practical situations where you want to actually come up with an approximate answer. So I'm using my calculator here to do log 13 and divide that by log 8. And I get 1.23. Solve to the nearest hundredth in this case. I've got to round somewhere, of course. I'll use the wave equal sign to say approximately equal to. And this technique will be handy a lot this week. Okay, let me forge ahead. You can pause and write that down if you like, and look at some basic models for dealing with compound interest. This is one place where exponential models are used a lot. And then we'll look at some more general models. The compound interest one is usually written this way. A equals P multiplied by the quantity 1 plus R over N all raised to the N times T. Let's annotate this a little bit, okay? So this is the initial amount. Actually, I think we can write it down here for reasons that will become clear. not the initial amount. This is the ending amount. In an interest situation, a financial situation where you are investing a certain amount of money over time. Here's what you wind up with. P is the principal, which is the beginning amount. Hope I'm seeing all of this on screen. Looks like it's in there, just barely. And then in here I have 1 plus R is the percent rate. And this is a percent written as a decimal. So 5% would be 0.05. And then we've got N that shows up 2 different places. Let's see. This is the number of compounding periods per year. Okay, both locations, N and N. Okay, and finally, T is the time in years. Okay, so an example of that, if you wanted to figure out how much money you have at the end of 5 years when you invest $100 at 5% interest, and it's compounded quarterly, meaning 4 times every year, so N equals 4, and this is at the end of 5 years, T is 5 years, you could plug all this in and you could crunch all this out. You'd probably want to do the stuff in the parentheses and then raise to the 20th power and multiply by 100. You'll find out how much money that $100 is worth at the end of 5 years, invested 5% compounded quarterly. I won't go ahead and go through that, but that's how that formula is used most directly. We've got some more interesting applications of it later in the weekly assignment. And then you've got a compound interest formula that isn't based on compounding a certain number of times a year, but compounding continuously. It turns out that if you explore this and you see what happens as you go from quarterly compounding to monthly compounding to weekly compounding to daily compounding to compounding every hour or every minute or every second, there's a limit to how much money you get out of this. Your $100 will grow faster if the interest is compounded more frequently, but there's like an asymptote above which you can't go. And so in modern days, most banks compound continuously. And the formula is actually simpler. This is same stuff here. The ending amount is still A. The principal is still P. The percent rate written as a decimal is still here, R. And the time in years is still there. I don't have the number of compounding periods, no N in my formula now. And this is actually the natural exponential base, approximately 2.718, right? That irrational number that's about 2.7. Turns out that E sort of shows up here when you look at that limiting amount for compound interest. So this is a little bit quicker. If you wanted to calculate what you get at the end of 5 years when you invest $100 at a rate of 5% for 5 years, you could just use this. E raised to the quantity 5 times 0.05 and then multiply that by 100. You'll get just a little bit more at the end of 5 years than you would if you were compounding quarterly. So keep those two formulas on the board. And let me add a couple other formulas. Actually, as you'll see, when you get through the section on compound interest, you kind of got the most important formula, because the other one you're going to see is a kind of a general exponential model. And this one is written A equals A naught e to the kt. Those are the letters the book uses. And what I want you to notice is that these two formulas are really the same formula. A sub 0 just means beginning amount, initial amount of something that's either growing or decaying at a constant percent rate over time. In this case, we're thinking money. We're thinking P is the beginning amount and it's principal for some initial investment amount. Here we could be thinking about a population of birds. We started with 1,000 birds and they were increasing at a rate of 2% per year or per month or per week per time period. We still have this e raised to the kt instead of rt. Over here, r stood for the percent rate, the rate of continuous growth, right? And k here is also the rate of continuous growth. But it's continuous growth, or it can even be rate of continuous decrease, continuous decay per time period, where this now could be in years, but it could also be another time period like hours or minutes or seconds. So really it's the same formula. And this is the one that we'll use a ton in general. All three of these are formulas you should memorize. There's one other formula at the top of the second page in the weekly assignment that is the logistic model. That one you don't need to memorize. You'll work with it a little bit, but you don't need to memorize it. If you need it in the test, you'll have the model right there. So basically these three models and this one, these two, do the heavy lifting. They're essentially the same formula in different contexts. Okay, let's see. I'm using a lot of time here, but let me apply this a little bit, help you with the week 10 written assignment. I'm looking at the blank assignment here and I'm thinking, like on page 1, item number 2 asks you to go through an analysis of how long 1,000,000 barrels of oil will last on planet Lek, right? And the heavy-dutyest part of this says, in which decade will the Lekians run out of oil? Okay, and they give you an exponential model for this. They give you t equals 2 to the n minus 1, and it says that the total oil consumed up to and including decade n is given by this formula. Set up and solve an exponential equation to figure out when the Lekians will run out of oil. Well, the total they have at their disposal is 1,000,000 barrels. So basically you have to solve this equation for n, right? Figure out what n is. And let's just add 1 to both sides to get this. And then to solve for n, what am I going to do? If I've got a variable in the exponent, I'm going to take a log of both sides. And you can take log base 10, or you can take a natural logarithm. And the next step, you're going to be able to pull that n down. And in the next step, you'll isolate n by dividing both sides by log 2. And then you can just evaluate this with your calculator to get a point in time when the Lekians are going to run out of oil. It's kind of interesting because what you'll see if you think as you're going through this, you'll see that I think in the table that you build, in decade 6 you use 32 barrels. So I don't suppose the Lekians would feel like they'd even scratch the surface of their $1,000,000 reserve in decade 6. However, as this process continues, the thing about exponential growth is it's very, very powerful. The rate of growth, the absolute rate of growth increases so fast that I think you'll find this is somewhere around, I think it's before the end of the 20th decade. You check it out. You could answer that question at the bottom. You could say it happened during decade 19 or before the start of decade 20, something like that. Let's look at some other problems in the weekly assignment and how you'd approach them. Let's see. Yeah, on the second page you get the models on the top and a number of questions. Let me start with a real easy one. So this is page 2, part 2, and let's look at number 3. And it just says, yeah, it gives you a model. It says a population of bacteria are growing so that the population is equal to 20,000 e raised to the 0.22 t. And I think the question here is just, what is the continuous hourly rate of growth of this population? Okay, well they set this up and they say, this is time in hours. This is the size of the population. This is the starting amount. Recognize the model basically. Eventual amount, starting amount, e to the kt. So this is the starting amount. We started with 20,000 bacteria. This is the continuous rate right here. So basically this is a question that you don't have to do any work on. It's right there. The continuous rate is growing at a rate of 22%. And they're growing at a rate, like a continuous compound interest rate of 22% growth every hour that goes by, because t is in hours. Let's go on to, I believe it's number 5, where they say, how long will it take the initial investment in number 1 to triple? And number 1 said, what's the account balance after $1,000 is invested for 5 years at 3.75% interest compound quarterly? Okay, so that first question is a direct application of this. You just plug in all the parts and crunch that on your calculator. But number 5 is saying, how long will it take to triple? So I put in the parts, and I'm starting with $1,000, and then I've got an interest rate of 3 3/4%, 3.75%. So that's 0.0375 as a decimal, 3.75%, divided by the number of compounding periods, and this was compounded quarterly, so 4 per year, and then raised to the 4 times t. I'm leaving t as time because I don't know how long it is. That's the question. How long does it take to triple? My starting amount was $1,000. If this is tripling, here's the other tricky part about this. I've got to figure out that my ending amount here is 3,000, right? So if I plug in all the information, how long does it take $1,000 to grow to $3,000? The one variable that's left is the t, and the fact that t is in the exponent means I'm going to take a logarithm of both sides to solve this exponential equation. Nevertheless, I'd make it simpler before I did that. So let's divide both sides by 1,000, and let's also crunch the stuff in the parentheses here. 1 plus 0.0375 divided by 4. Enter. Okay, so I've got 1.009375 raised to the 4t. I would get to this point before I took a log of both sides. Clean it up a little bit. And then let's take a logarithm of both sides. And I'll take a natural logarithm because it's the least writing. I usually work with a log or an ln. I could do a log of any base, but those are the two that I have a calculator key for, so it's kind of convenient. And then I'm going to take a log of both sides on over here. Actually, let me squeeze in 2 steps here. I'm going to take a ln of this side, and I'm going to use the property of logarithms that allows me to take the 4t that will be inside the logarithm and pull it down outside, right? And I'm trying to isolate t, right? So I'm going to wind up with a natural logarithm of 3 divided by, well, t is just multiplying two numbers here. It's multiplying 4, it's 4 times t times the natural logarithm of this stuff. So I'm just dividing both sides by 4 ln 1.009375. Let's see what I get. That's equal to t. So with the calculator, this is approximately, oh actually I already did this, 29.43 years. Of course I'm going to want to label that. So that's answering that question about how long it takes to triple. And other than the technique of taking a log of both sides to get this out of the exponent and solve, the main trickiness was using that tripling thing to say, oh, if I have a starting amount of 1,000, I'm going to wind up with an ending amount of 3,000. Let me go on to an example on the next page. Let's see, I wonder how I'm doing for time here. Actually, I think I'll stop now and do a second video with a couple more examples from the assignment.